Welcome back to ECE 441A, 541A. Your passports were due last night, but if you didn't get those in, I don't believe I've closed up or locked up the Dropbox, so please make sure and get that submitted. You still have a few days to take your pre-quiz, which is, I think that's a Sunday, the 5th. Or is that a Monday? I can't keep track of my days. And homework number 1, it has been assigned, and that's due on the 11th. What I want to do today is get very comfortable playing with different ways of representing or modeling this mass spring damper system. Even though we're doing it for the mass spring damper system, these techniques can be applied to any system that you're playing with, as long as you're starting with the appropriate information. What we want to do today is start with the differential equation and derive the transfer function. So I'm going to be abbreviating these possibly as DE to TF, and then you can text it more quickly if you're needing to send this information somewhere. You can say DE to TF, and they know exactly what you're talking about. You're transforming or translating differential equations into a transfer function. Then we will start with a block diagram and transfer that into a transfer function. Then we will start with the state space and derive the transfer function. And you can then figure out different ways of moving back and forth between these so that we can actually do a dance relative to all of these different two-letter acronyms. We can go block diagram to state space to transfer function to differential equation, etc. So that's what we want to get comfortable with, and then we will talk about the Bode plot for this if we get that far, and if we don't, then you'll have to start remembering what it is to do a Bode plot, how to sketch that if you're given a transfer function. And next time we meet, which is Wednesday, we will develop these differential equations, the equations of motion, for a more interconnected system, and in particular a three-mass system. And it will have different springs and dashpots interconnecting it. This I'm assuming you have already implanted in your brain for this semester. It's this system, which is a mass spring damper system. And what we want to do is then, as we said, go with different ways of describing this into a transfer function. And let's start then with the differential equation, and you can probably say this from memorization, what this differential equation is. This is now m s squared. Whoops, what am I doing? I'm already going into the frequency domain. Sorry. Let's do the time domain. This is m, the mass, times the acceleration, plus the dash pot times the velocity, plus the spring constant times position, and that's equal to gamma u of t. And sometimes I will neglect to put the arguments on the signals, but hopefully from the context you will know whether we're in the time domain or the frequency domain. In this case, we're in the time domain with our differential equation. And if you don't remember that, you should be able to actually sketch a free body diagram and quickly do a sum of forces, and then remember what the different forces are relative to a damper, a spring constant, and inertia, and all of the externally applied forces. But this now describes the time domain behavior. It's not the solution. This just tells you the way the system behaves dynamically. It's governed by this differential equation. Let's now take this from the time domain and go into the frequency domain. Or we're starting on this path to derive a relationship between the differential equation to the transfer function. And in the frequency domain, since we are wanting the transfer function, we can actually neglect the initial conditions. Later on, when we start with the state space, we'll go ahead and include the initial conditions initially and then neglect them later, but that way you can see where they are or how they impact the particular representation in the frequency domain. Here, we're simply going to neglect the initial conditions because all we want is the transfer function. And what we need to remember is how to transform derivatives from time domain and get those into the frequency domain. So if I have a derivative in the time domain, what does that look like in the frequency domain? That's multiplication by s. And if I have two derivatives, now I'm multiplying by s squared. Three derivatives, s cubed. With that concept in mind, now we can quickly write down the frequency domain, or the Laplace transformed representation of the dynamics based on this differential equation. M is a constant, and so that slides through the Laplace transform when we have ms squared capital X of s plus b s x of s plus k x of s is equal to gamma u of s. And to find the transfer function, let's just combine or factor out the variable capital X of s, and we have s squared m plus sb. See, I didn't want to have any bs today, so I said sb plus k times x of s is equal to gamma u of s. And if we want the transfer function, we are wanting to then look at the ratio of x of s to u of s, and if we isolate that on the left-hand side, that produces our transfer function g of s, which is now gamma over s squared m plus sb plus k. And sometimes we will actually potentially want to normalize the leading coefficient in the denominator, meaning factor out the mass. If we factor out the mass from all the terms in the denominator and actually push it upstairs, we could have an equivalent transfer function as gamma over m s squared plus b over ms plus k over m. And we've then just gone from a DE to a TF. We've gone from a differential equation to a transfer function. And that was pretty easy. That's pretty clean. Let's look at another way of finding a transfer function based on starting with a block diagram. And here, I hope it's clear, but a lot of this I'm maybe just doing without saying, but we need to make sure that we're keeping track of the processing blocks or the systems, the 1 over s's, the gains, gamma over m, and make sure that those are, that those are different from the signals in the system. The signals are anywhere you see one of these lines. That could be a signal. Here, to make it consistent with what we've done earlier, let's go ahead and say the output is the position, capital X of s. Then we have, let's say, x sub 2 of s coming out of the first integrator in the frequency domain. And I will go ahead and absorb the negative sign into my gain so that all of my inputs to this summing junction are positive, and I don't have to label what those are in terms of their sign. But in general, if it's not labeled, you should be able to just assume that all of these have a positive sign going into that summing junction. Yes. So this we've already, maybe somebody just, so the question was, where did this block diagram come from? At this point, you can say, oh, I was just given this, but in some cases, you may have already tried to derive this, and we developed this last time from the equation right there. From this particular frequency domain type relationship, you can actually derive the block diagram. And we'll start to get more comfortable doing that. So it depends on really what you're starting with in terms of information. In this case, in this example, what I'm assuming is somebody just gave us this block diagram, and now we want to find the transfer function. But in general, you might have to sketch this based on, we actually found it from the differential equation and started with an all-integrator block diagram, and then we put that into the frequency domain. But now that we have this, what we want to do, assuming that we just have this, we want to try to find the transfer function. I'm going to erase those positive signs because I said that I might neglect those and just assume that those are positive coming in. And now what I want to do is derive the transfer function starting from this block diagram. And a lot of times it's actually easier to write your equations in terms of the signal coming out of the summing junctions. Here we really just have one summing junction, and I'm going to label that arbitrarily as a Laplace transform signal, capital W of S. And if you wanted to, you could sort of think of this as, oh, I want to find this signal beta in terms of this signal alpha 1, this signal alpha 2, and this signal alpha 3. Meaning I'm really trying to just find the governing relationship between all of these variables just by looking at that summing junction, which says that beta, the output of that summing junction, is equal to those three signals, alpha 1, alpha 2, and alpha 3. And now let's just find those or rewrite those. Beta is just our W of S that we arbitrarily wrote down. We just said, let's label that signal as some variable, and I'm just going to label it as capital W of S. Now, what's alpha 1? Alpha 1 is a signal, and that's made up by really filtering or scaling the signal coming into that block. And in this case, it's just a gain, gamma over m, which adjusts the level of U of S to generate alpha 1. Alpha 1 is simply gamma over m U of S. Then alpha sub 2 is the output of that gain block, the lowest level gain block, and that's just minus k over m, and that minus k over m is going to scale capital X of S. Or I now have minus k over m X of S. That's just alpha sub 2. I never know which part to show because I don't want you to forget this, but maybe you have that in your notes. And you need to tell me where the lowest is on the screen, maybe it's clear up here that you can see in the back row, then I'll just have to write one line and start scrolling. Just joking a little bit, but please let me know what you can or cannot see. And it depends on how this classroom is laid out, which it doesn't have a sloping floor, so it's a little bit more of a challenge. Alpha 3. What's alpha 3? That's simply minus b over m x sub 2 of s. But now we've maybe made our lives more complicated because now we have a w, we have a u, we have an x sub 2. Now what do? I can't get a transfer function with all of those variables floating around. A transfer function, I need a ratio of 2 signals. Let's now make that like it was before. We want the output, capital X, over u. So that now if we go back here, we can find how to relate x sub 2 and x sub 2 and w to find x. Meaning x sub 2 is an input, so let's write it a different, well, I can write x sub 2 as 1 over s w of s. And in fact, that's the frequency domain integration of w of s. That's x sub 2 of s. And x of s, likewise, is a filtered version of x sub 2, where the filter or the scaling is 1 over s. But if we now know that x sub 2 is 1 over s w of s, we can combine those so that we now have 1 over s squared w of s for x of s. This now gives us a relationship, actually two relationships in that one equation, relating x sub 2 to x and w to x. So that now if we want w, or if we want to rewrite w in any of our equations in terms of s, x, that's now s squared x of s. Likewise, x sub 2 of s is s x of s. And what we want to do now is rewrite our earlier equation, the beta equal alpha 1 plus alpha 2 plus alpha 3, and replace the w and the x sub 2 with these relationships involving x. And that relationship then said, oh, we had w, which we now know as s squared x of s, and that was equal to gamma over m u of s minus k over m x of s minus b over m s x of s, where the b over m was weighted by x sub 2, and we know x sub 2 is just s x of s. Again, if we reposition the terms in this expression and put all the x terms on the left and the u on the right, we can now have s squared plus b over ms plus k over m times capital X of s is equal to gamma over m u of s. And to find our transfer function, we can divide both sides through by that s squared polynomial, and we can divide both sides by capital U of s. We now have x over u is equal to gamma over m s squared plus b over ms plus k over m. And hopefully that's the same transfer function that we started with, or that we found, going directly from the differential equation to the transfer function. That was dE to TF. This is now block diagram BD to TF. Let's look at doing it one more time, starting with a state space representation. And this you may already have memorized. This is x prime of t, x double prime of t. That's the state vector differentiated. Our state was x and x prime, position and velocity. Differentiated once gives us the vector, or I guess what I did do before is, let me write it in terms of state variables, so that I now have x1 prime and x2 prime. That's equal to something times x1, x2, the state vector, plus something times u of t. x1 prime was just x2 and no input, meaning the top row is 0, 1, 0 in the system matrix and the input matrix. And in the bottom row, we had x2 prime, or the acceleration, was equal to minus k over m times the position, which was x1, minus b over m times the times the velocity, which was x sub 2, plus gamma over m times u, where this is our A matrix, the system matrix, and there's our input matrix B. And last time, and to be consistent with everything else, we said our output was just going to be the position variable, which in the state space representation was x sub 1, and there was no input directly feeding through into the output y. So our D matrix, or the direct feed through matrix, was 0. And if we wanted to write this in a more compact form, then you could say, oh, the state space representation, that's x prime equal a x of t plus b u of t. Y of t is equal to c x of t plus d u of t. And now, depending on the system, that will determine what your vector is x, what your input vector is u, and what your a, b, c, and d actually are. In this particular case, A is 2 by 2, and it has the structure that we've indicated. B is a 2 by 1, etc. But now what I want to do is actually work with this more general description and Laplace transform that in general, and then when we get a little bit further into that process, replace the A, B, C, and D matrices with what we know they are in this example. Let's now Laplace transform that differential equation. And I'll cheat a little bit. I'll do the easy step. Oh, here's the Laplace transform of the left term. Laplace transform of x prime. At least you might get a point out of 50 on the exam if you did that. Then that's equal to the Laplace transform of the right-hand side. which is A x of t plus B u of t. And remember that we're assuming that this is a time invariant system, or that these A and B are constant matrices. Now we need to go back and actually perform this Laplace transform. This was just sort of a shorthand to keep me honest as far as what do I now need to do. What happens when, in general, you Laplace transform a derivative? We multiply by s, but now I want to do it more generally. Did you have any other term besides s x of s if you were now Laplace transforming a derivative? You had the initial condition term, didn't you? So this was now minus x of 0 minus. And that 0 minus is the value of the signal x, the state vector. And now x, remember, is a vector that's 2 elements tall, or it has 2 coordinates. It has a position, that's x1, and it has a velocity x sub 2. That's absorbed or hidden in that description, but this is for the time t equals 0 minus. Then we have A, that's a constant matrix, times the Laplace transform of x of t, plus B times the Laplace transform of the input, which could be generically an input vector. And I'm just, in that particular step, I'm simply emphasizing the fact that A and B are constant, and so they can be factored out of the Laplace transform operation. Or the Laplace transform slides through, and all we have to do is Laplace transform those time domain waveforms. And in fact, it's not too hard to finish, because we are just calling the Laplace transform of little x of t as capital X of s. Similarly, we are simply calling the Laplace transform of u of t capital U of s. And let me just emphasize or make that remark. X of s is actually a vector, and in general, it's a vector that's in coordinates tall, or in elements in its vector, in being Nevada. So if you can't tell whether I'm saying in or m or something else, I'll try to say something, maybe a state. So this one's Nevada by 1 in terms of its dimension. And in our example of the mass spring damper system, how big is Nevada? How big is n? 2. Now, what I want to do is work with this to try to find a transfer function. Now I'm in the frequency domain, and I'm trying to go from state space, SS, to TF transfer function. On my way there, I'm actually keeping track of where I started with my initial condition on the position and velocity. But when I want my transfer function, I'll simply neglect that in a minute. First, I want to combine all of the terms that have similar signal vectors multiplying them. And here, what is S? Very vague question, but S is a frequency variable, and it's a scalar. Now I have a scalar S times this n by 1 vector x of s equaling an n by n matrix A times an n by 1 vector x. So when the multiplications happen, I'm still okay, but if I wanted to try to factor out this capital X from those two terms, I actually need to introduce a placeholder, the identity matrix. in between this scalar s and this n by one dimensional vector capital X. I haven't changed anything. I've just now introduced a placeholder I, which is the n by n identity matrix. Nevada by Nevada. And if you go home and you multiply S times capital X of S, or SI X of S, you'll get exactly the same result. But I need that placeholder so that I can now factor out capital X of S between or in this first term, SI. I want to pull that A X of S to the left. I now have minus A times X of S. Let me put the initial condition on the right-hand side, meaning I'll add little x of 0 minus to both sides, and I still have to keep track of B U of S. All I'm doing is manipulating or some algebra on this transformed equation. And I still have just an n by 1 vector on the left side and the right side after I've performed all of the multiplications. Now I might want to find capital X of S, or isolate it, and I can do that since Si minus A is a matrix. I can now find or solve for capital X of S by multiplying on the left everything by Si minus A inverse. How many terms do I have on the right-hand side of that equation? What is this? This is actually telling me, this equation says, oh, the Laplace transform of your state vector, the Laplace transform of x1, which was position, and the Laplace transform of the velocity, x sub 2, are all buried or hidden in that capital X of S. I've now found those in terms of the initial condition, x of 0 minus, and the forcing function, u of s. I've now found the two parts of my total solution. My position and velocity are made up of some term due to the initial condition, you could call that the initial condition response, and a term due to the input, which you could call the forcing response. This is now the initial condition, let me just say piece or component, and this is the forcing function piece. Or maybe I want to write this in terms of my output, so that now I need to start with the output equation. Since at some point I need the relationship between the input and the output, I now Laplace transform the output equation, which is the Laplace transform of y is equal to the Laplace transform of c x of t plus d u of t. Do I have any dynamics in this equation? Is there any derivative? That's how I am sort of measuring or commenting on dynamics. Do I have any dynamics or derivatives in this output equation? No, this is just a linear combination of state variables through the output vector C and inputs through the direct feed-through matrix D. These are all just non-dynamic. It's simply a relationship that provides us with the output, which allows us now to say that capital Y of S, the Laplace transform of the output, is C times x of s plus d times u of s. And what I want to do now is substitute this x of s right there. All of that right-hand side I want to put in right here for capital X of s, which allows me then to find my output y of s in terms of initial conditions and outputs. I have c times si minus a inverse x of 0 minus, that was the initial condition piece, plus c si minus a inverse b times u of s, and I can't forget this piece, the du of s, plus d u of s. Which now, if somebody gives me the Laplace transform of my input, which is capital U of s, and the initial condition, I can give them Laplace transform of the output, and if I inverse Laplace transform, now I know the output as a function of time. Just given the input and the initial condition. If I want the transfer function, how does that simplify this expression? What have I done before when I'm just wanting the transfer function? The transfer function between the input and the output. I can ignore the initial condition. And I want now to find that transfer function. I'm trying to find TF, which means that the terms that involve the initial condition I'm going to neglect. And I now have the output y of s is c si minus a inverse b u of s plus d u of s, but now I can combine that or factor out the common input Laplace transform, and I have c si minus a inverse b plus d u of s, and this is my transfer function, capital G of s, in terms of my a, b, c's, and d's. So you could, not that I want you to, you could forget what we just talked about and have this written down on your note sheet on the exam, and you could now find the transfer function G of s in terms of the state space representation. It's the output matrix C times this matrix inverse, Si minus A, S is a variable, times the input matrix B plus D, and that gives you your G of S. Let's now relate this. So that's the generic transfer function for a standard state space representation. You give me a robot described in terms of A, B, C, and D, and I can use this to find the transfer function. You give me a car that's modeled in A, B, C, and D. I can now give you its transfer function. You give me a circuit. You give me a mass spring damper system. I can find a G if you give me the A, B, C, and D using this expression. In our particular mass spring damper system, was there something that was simplified in this A, B, C, and D expression? Were any of those zero in our mass spring damper system? D. And now I'm remembering something that's probably confusing everybody. So let me point that out. This B is a 2-by-1 vector. That's not the same thing has this b, which is a scalar constant. Okay? So if you're listening, I just made a face. Make sure that this b in my mass spring damper is not confused with the input matrix b in the standard notation. That should be clear from context. But yeah. That being said, let's plug in this expression. We now have g of s is equal to c si minus a inverse the matrix b, and we said d was 0, so this is now our transfer function. And since this is the fall and we have maybe games going on the weekends, we may want to start cheering. So this might be one of our cheers. C, Si minus A inverse B. And we'll have other ones. But now you know this cheer. If I say, give me a G, you'll scream out, C, Si minus A inverse B. Right? It's like this, U of A. Except I go G and you go C, Si minus A inverse B. You won't forget that. Now you know the expression for the transfer function in terms of A, B, and C. Okay? And this is assuming what? This is assuming your direct feed-through matrix D is 0. And I apologize for those that are listening. You didn't see that cheerleader leading, but that we spared you on that. Now, let's plug in what we know is true for our example. What is C? The matrix C in our example. What was it in terms of a matrix? It was a 1-row by 2-column matrix, wasn't it? And its entries were 1, 0. That was C. Now we want S times the identity matrix, and the identity matrix was 2 by 2 minus A, and the A matrix was 0, 1 minus K over M minus B over M, and all of that expression is inverted, matrix inversion. So now we have a symbolic matrix inverse to perform. And then B was 0 gamma over M. It was a 2 by 1 matrix. On the exam, if I give you an A matrix that's 6 by 6, you should be able to invert it symbolically. Is today the last day to drop? I'll request a smaller classroom, and I'll let you know when we get it given to us. But now let's look at finding that matrix inverse. And your calculator, some of those will do this symbolically. Your Inspire calculator can do that inverse for you. Let me say this is an aside. Let's look at finding, and now let me scale that identity matrix with the scalar S. It's now S00, 0S, and if I push that negative sign through my A matrix, I now have 0 minus 1, K over M, B over M, and I want to invert that expression. And if I combine those two matrices, I now have S minus 1, K over M, S plus B over M, and I want to invert that. Is everybody okay with what we've done so far? And an inverse of a matrix is just 1 over the determinant of that matrix times the cofactor matrix. Actually, the cofactor matrix transposed. Okay? It's the adjoint matrix. So let me now find the determinant. What's the determinant of a 2 by 2? Diagonal multiplied minus the off diagonals multiplied together. So now I have S times S plus B over M minus 1 times K over M. There's my determinant. And if you multiply that out, you'll end up with S squared plus B over MS plus K over M. That was in the denominator of our G of S, wasn't it? Now what we want to do is multiply that times the adjoint matrix, which is the cofactor matrix transpose. So let's just find the cofactor matrix and transpose it. Now, what's the cofactor matrix? Well, we have to identify the cofactors. To identify the cofactor associated with the 1, 1 entry, I come up here and I say, okay, let me eliminate the first row and let me eliminate the first column. That's the 1, 1, and take the determinant of what's left over. That's S plus B over M. But in this cofactor matrix, I need to scale it by minus 1 raised to the 1 plus 1, which was the 1, 1 entry, times S plus B over M. That's the 1, 1 entry in my cofactor matrix. Now, if I want the 1, 2 entry, that's the first row, I get rid of that. I get rid of the second column and I find the determinant of what's left over. In this 2 by 2, it's easy, isn't it, to compute the determinant of a scalar. But in general, it would be the determinant of that matrix, that submatrix that's left over. What's left over when I eliminate the first row and the second column? K over M. But consistent with what I had before, I now have minus 1 raised to the 1 plus 2. That was the first row, second column. Again, I have to transpose all of this after I'm done. Now what do I want to do? Let me do the 2, 1 entry cofactor. So the second row, first column, and I find the determinant of what's left over. That's minus 1, but I need to scale that by minus 1 raised to what power? 2 plus 1. Second row, first column. Finally, if I want the cofactor of the 2, 2 entry, I have minus 1 raised to the 2 plus 2, minus 1 to the 4th. That's just 1. But what's left over that I have to scale by? That's just S. If you allow me to call the determinant delta in our aside, I now have 1 over delta times this cofactor matrix transposed. The diagonal doesn't move, does it, when I transpose? I just flip across the diagonal. Up in the 1, 1 entry, I have S plus B over M. In the 2, 2 entry, I have S. What's in the 1, 2 entry? I have minus 1 raised to the third power. That's minus 1 times minus 1. That's 1. What about the 2, 1 entry? That's minus K over M. Now do you see the trick for a 2 by 2 matrix? If I started with this beast right here, S minus 1 K over M, S plus B over M, and I wanted to invert it, I divide by the determinant, that's easy to compute, and then I interchange the diagonal terms and negate the signs of the off diagonal. That doesn't work for anything but a 2 by 2, but that's what you have. That was our aside. What I want to do is now put all of that together, and we now have g of s is 1, 0, s plus b over m minus k over m, 1s times 1 over delta times 0 gamma over m. And that 1 over delta is a scalar. I can pull that out, do all this multiplication, and I'll end up with a transfer function that better be the same as what we derived for the other cases. I'll let you finish that up. I might finish it up in the notes, and we'll pick up at that point next time.